Okay, so I have to leave town next week, so I'll be here Monday morning. I'll be here all Monday. But I got a bunch of meetings all day and class, so there'll be class on Monday, and then I'm on for the rest of the week. So no class next Wednesday, no office hours I have no office hours. So the TA Richard should still hold. Okay. Any questions on the material we've been covering so far? 1D parity checks, 2D parity checks. Everybody's all set with that? Okay, today we're going to move on to linear Hamming codes. But before we do that, let's talk about something that's known as the Hamming distance. Anyone familiar with this? It's a real simple idea, but let's do some very elegant things. Okay, first we're going to define the Hamming distance h of u comma v between two k-bit strings. Okay, so what I mean is that u is a1, a2, a3, dot, 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 ak. V is b1, b2, dot, 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 bk, where ha sub I is either 0, 1, hb sub I is either 0 or 1. The Hamming distance from two strings is h of uv equals the sum from I equals 1 to k of indicator of ai not equal bi. Okay, where I mean by this is indicator of true is 1, is 0. Okay, so for instance, the Hamming distance between 0, 1, 1, 0, 1 and 1, 1, 1, 0, 0 is what? 2. Yeah. So intuitively, it's the number of bits in U that must be flipped to get V, or the number of bits in V must be flipped to get U, and the process is reversal. Okay, so if you want to get here, if you want to get V from U, you flip the first bit, you flip the last bit, right? So the distance of anything with itself is going to be 0. You don't need to flip any bits, right? Right, e.g., Hamming distance of 0, 1, 1, 0, 1 and 0, 1, 1, 0, 1. How many bits do I need to flip to go from 0, 1, 1, 0, 1 to 0, 1, 1, 0, 1? 0. Right? And Hamming distance of U not U is k, where k is the number of bits in U. Right? The Hamming distance between 0, 1, 0 and 1, 0, 1 is 3. Everybody got it? Okay. Let's talk about valid code words for a minute. a protocol will send a sequence of bits. In a code. Okay, this is not like a secret code. This is error predicting code that we're dealing with here. So a sequence of bits in a code to deliver a message with increased reliability. For instance, we did the 1D parity check code. Okay, the code is going to be a K data bit and one code bit with a code bit is the XOR of the data bits. Right, we saw that last time. Right? So for instance, if, so example inside of an example, if 0110101 is the data, 0110, how many we got? 4 ones. 011011010 is the code transmitted. Right, where this here is the code bit. Right, both the sender and the receiver know that it's the last bit that's going to be the code bit, and it's the exclusive OR of the data bits. Everybody with me? Everybody with me so far? Okay, so is the code transmitted, and it's called the code word. Okay? Everybody with me? It's called the code word, so we're going to be using the term code word a lot. A valid code word. For a protocol, P is a sequence of bits that the protocol sender can legitimately send. Okay, so for instance, going back to the 1D parity check. Zero one one zero one zero one, okay, is a valid code word. Okay, I mean here we've got, these are the data. This is the code or check bit. Okay, and it's the right check bit, right? This is what the sender would send. Okay, whereas 0100101 is not a valid code word. Right, because here's your data, and here's your check bit. Something's wrong, right? The sender would never send this. It doesn't follow the protocol. Right, so it's not a valid code word. Okay? So now you know what the Hamming distance between two bit sequences is and what a valid code word is. What next? Okay, well, a protocol applied to k-bit data strings. I should say protocol. I'm not so crazy about protocol. Let's say an error detecting / correcting code. Detecting / correcting code applied to k-bit data strings produces a set of valid code words. N-bit valid code words where n is going to be greater than k. Right? So for instance, for the 1D parity code, n is k plus 1. Right? You're always attaching 1 bit. For the 2D parity check, n is k plus, however long you make your row, plus however long you make your column, plus 1. Right? Okay, produces a set of valid code words n greater than or equal to k. In fact, how many valid code words will there be? Assuming any data sequence is valid. Two to the n is the number of possible code words, but they're not all necessarily valid. Two to the k, yeah. There are 2 to the k valid code words. One for each possible sequence of k data bits, right? So for instance, suppose k is 2, and we use 1D parity check. Okay. Valid data sequences. Are what? Well, any sequence of 2 bits is a valid data sequence. 0, 0, 0, 1, 1, 0, 1, 1. Right? So what are the valid code words? Well, when I try to send 0, 0, the valid code word is going to be 0, 0, 0. Right? The 2 data and the check bit. For 0, 1, it's going to be 0, 1, 1. For 1, 0, it's going to be 1, 0, 1. And for 1, 1, it's going to be 1, 1, 0. Right? What are other code words? Well, in this case, I've got 4 invalid code words, right? So invalid. 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 1. Those are the invalid code words. Okay. The Hamming distance of a code C applied to k-bit data sequences is, all right, we're going to say h of C, now let's say h of c. The Hamming distance of the code is going to be the min, that's real big, the min over, so let's say h sub k of c, to imply it's for k-bit code words, because some codes like the 1D parity check can be applied to any length string, and it turns out to have the same Hamming distance regardless, but that won't always be the case. Anyways, the Hamming distance for k-bit data sequences for that code is the min over let's do it this way. U comma v are k-bit strings u not equal to v. So they're two different strings, k-bit strings, of the Hamming distance between the coded u and the coded v. Okay? Equivalently, okay, let, what do I want to say? Let's call it S. S sub k of C be the set of valid code words of code C applied to k-bit, applied to all k-bit data sequences. Okay, then equivalently hk of C is again the min over u comma v, both in this set sk of C, again u not equal to v, of h. Let me not use uv, let me use x and y. H of x, y. The Hamming distance between h of x and y. So what am I basically saying here? I.e., take all valid code words, find the minimum distance between pairs of valid code words, and that's the Hamming distance. Of the code. Okay, so you can have a Hamming distance between two strings, and then we also just talk about the Hamming distance of a code, which applies this Hamming distance between two strings. So for instance, suppose for code C, the valid code words are 00000. Suppose those are my valid code words for the code. What's the Hamming distance for this code? What's the Hamming distance between this pair? 3. And what's the Hamming distance between this pair? 3. And what's the Hamming distance between this pair? 3. And what's the Hamming distance between this pair? 4. And what's the Hamming distance between this pair? 4. And what's the Hamming distance between this pair? 2. So what's the Hamming distance of the code? 2. It's the minimum. It's the minimum distance between, it's the minimum of Hamming distance between all pairs of valid code words, right? Excluding a valid code word with itself. Okay? So you got the Hamming distance? Okay? Okay. Suppose now, again using this code, okay? And a receiver receives the transmission zero 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 one one. Okay? It's not a valid code word, right? It's not a valid code word. It means there have been some bit errors in transit, right? Okay. Well, suppose bit errors are very unlikely. What was probably the code word that the sender was trying to send? 00111, someone said. Why? Why do you think that's the one they were trying to send? The Hamming distance is only 1. It's the closest Hamming distance. In other words, you have to flip the fewest number of bits to go from a valid code word to this code word if you start with 00111. Right? So the idea is if bit flips are very unlikely, you probably want to pick and you know some valid code word was transmitted and you received an invalid code word. You want to pick the valid code word whose whatchamacallit, Hamming distance minimizes the number of bits you have to flip to get here, which is the same number of bits you have to flip to get back to that valid code word. Right? So the error correcting method is choose the valid code word that minimizes. Choose the valid code word U that minimizes H of UV, where V is the received code word. Right, and of course, if you receive a valid code word, you don't flip any bits because the Hamming distance is 0. You just choose that code word itself. Right? So here's a really cool theorem. And when I first saw this, I was like, what? So weird or so neat. But with everything we've talked about so far, it's actually obvious and easy to prove. So, a code with Hamming distance D, okay, can always detect, well, I should say that applies, just detect, can always detect up to D bit flips. Okay, and if the protocol applies the correcting technique above, okay, always choose the valid code word with whose Hamming distance is close to the received code word. Then a code with Hamming distance let me say it this way. Code with Hamming distance 2D plus 1 can correctly correct, will correctly correct up to D bit flips. Okay, so a code with Hamming distance 7 can correct, can detect any 7-bit flips. So I transmit a message with this code with Hamming distance 7. If 7 of the bits or fewer are flipped, I can detect that 7 of the bits or fewer have been flipped. Okay? And can correctly correct any 3 flips. So the code, you'd be able to, by using this method, you correct any 3-bit flips. And I'll show you a graphical proof. So you'll doesn't that seem kind of cool? Do people see why, or not yet? All right, you'll see why in a minute. So I'm gonna draw. Let's look at the code words. Our nodes in a graph, connected by an edge. If they have Hamming distance 1. Okay, so I'm just going to have a bunch of code words, valid or invalid, right? All 2 to the k of them, or 2 to the n of them. N is the length of the number of bits in the code word. Okay, and if they have a Hamming distance of 1, I connect them. Okay, so this is just some weird code. Okay, this is the code. There's no reason why it has to be a planar graph, but it's just easier to draw. I don't want it to get too messy. Okay, and some of these code words are valid. Okay, so I'm going to circle the ones that are valid. Let's say this code only has 3 valid code words. Okay, so I've circled the valid code words. So what's the Hamming distance of my code here? The Hamming distance of the code is the shortest path between 2 valid code words, right? Because in order to get from this code word to this one, I have to flip a certain number of bits. And every time I flip a bit, I'm moving Hamming distance of 1. Right? So when I flip a bit, I move from this code word to some other valid code word, to some other code word, right? People see how I'm moving in this graph. When you flip a bit, you move to, if you change the code word, and you're only changing 1 bit, so you have to move Hamming distance of 1. So I move to I'm basically just transiting an edge in the graph, right? And so the Hamming distance between 2 valid code words is the shortest path between those code words in the graph, right? It's the fewest number of bits I have to flip. When I flip a bit, I go Hamming distance 1. So it's the fewest number of bits I have to flip to get from one valid code word to the other. So in this graph, I have a Hamming distance of 1, 2, 3, 4. 1, 2, 3, 4 between these 2 code words. 1, 2, 3, 4 between those. I think that's the shortest path. And 1, 2, 3, 1, 2, 3, 4 between those. So I've got a Hamming. Here I've drawn a graph with Hamming distance, a code with Hamming distance 4. Right? People with me? Okay. Well, the sender is going to set out some valid code word, right? And the only way the receiver can be tricked, can receive not realize that there's been an error, is if it receives another code word that's valid. That's the only way to trick a receiver. If a receiver receives an invalid code word, it's detected an error, right? So how many bits do you have to flip to trick the receiver? You've got to be able to move from one valid code word to another, right? If I only flip 2 bits in the valid code word, I'm only going to get to some other invalid code word. The receiver is going to know, right? I've got to move from one valid code word to another in this graph in order to trick the receiver, right? So that's why if the code has Hamming distance of d, you're going to have to flip d bits before you can trick the receiver. I said up to d bits. Sorry. Can detect, it should be d minus 1. My mistake. Right, so if I flip d bits, I actually move to the next valid code word. Right, and I can trick the receiver. But if I can only flip d minus 1 bits, I can only move across d minus 1 edges in this graph. I can't go from one valid code word to the other. I'll either wind up back at the same code word, in which case there was no error, or if I flip no bits, I'll never leave here, in which case there was no error, or I'll wind up at some invalid code word and the receiver can detect that the code word is not valid. Right? But the receiver will get a code word that's not valid, so it'll know there's been a bit flip. Okay? What about our correction routine? Okay? Basically, the correction routine says always go back to whenever you're at a code word, always move to the closest invalid. So if you're at an invalid code word, always move back to the closest valid code word. Right? So if I receive this code word, I know to move here. If I receive this one, I'm not really sure where to go. It's 2 hops to get to this valid code word. It's 2 hops to get to that one. So I can't really correct the error accurately every time. Yeah, Sebastian.
Does it also mean that the distance between invalid code word and valid code word has to be like d minus 1 as well? Like, I mean, you can have a graph that goes out, somewhere and just takes off.
Goes out and takes off.
You have like a couple more edges on the left side, so that the distance, between between like an invalid code word and a valid code word is like more than D minus 1?
Well, that doesn't matter. So I've got a bunch of invalid code words that you have to flip a lot of bits to get to. So what? Suppose I'm sending out a code where my only valid code words are 00000 and 11111. Okay? I'm claiming that this code, you need to flip 5 bits. It's got a Hamming distance of 5. You need to flip 5 bits before you can fool me. Right? That's clear. Okay? Suppose that's not an example. I'll show you what I'm talking about. Suppose I give you the code words, the valid code words are 00111 and 11111. It's a stupid code because the last 3 bits are meaningless. Suppose you receive the sequence 10000. Okay, this code word is far away from any valid code word. So what? I mean, I know it's wrong. It's just really wrong. But so it's one of these. It's just saying that the code itself is not well designed. You're kind of wasting your bits. Okay. Okay. So now going back to correction. Remember the routine is if I'm at an invalid code word, I always move to the closest valid code word. Okay. So the idea is that if I have a number of bit flips that take me less than half the distance to the next valid code word, then when I apply this routine, I'll always go back to my original code word. And hence that's the 2D plus 1, right? A Hamming distance of 2D plus 1 will correctly correct up to D bit flips, right? So imagine, unfortunately my code had an even Hamming distance, right? But imagine it was odd. Then suppose the Hamming distance was 5. So in order to get this valid code word, I have to flip 5 bits to get to any other valid code word, right? If only 2 bits get flipped, I'm still closer to this code word than I am to any other valid code word. Hence, when I apply the correcting routine of always going back to the code word with minimum Hamming distance, I'll go back to my original code. Okay, so the D in the 2D plus 1 just means the number of bit flips you're taking takes you less than half the way from your valid code word. So when you apply the routine where you go back to the valid code word, to the closest valid code word, it'll take it back to the right one, right? And once I cross the halfway point, okay, I'll go to the wrong code word. Hence, this routine of always going back to the closest one will send me to the wrong code word if I flip more than the minimum Hamming distance number of bits. If the Hamming distance is 2D plus 1 and I flip D plus 1 bits, there's a good chance I'll be close. It's possible I'll be closer to another. There exists an instant where I'll be closer to a valid code that's not the one that was intended to be sent. So it won't correct it correctly. Okay? Okay, so let's look back at the single bit parity check, or the 1D parity check. 1 parity check. Okay, has Hamming distance of what? Not 1, 2. Yeah, you have to flip 2 bits to move from one valid code word to the other, right? And an example is here's a valid code word. That's not valid. Here's a valid code word, and here's another valid code word. And I flip 2 bits to get from one to the other, right? So an instance, a 2-bit flip instance, Right, the Hamming distance between these two valid code words is 2. And it's pretty easy to convince yourself that 1 bit won't work because obviously you'll change the parity of the correction. So it has Hamming distance of 2, which if you go by the formula means that it can detect up to 1 bit flip, which we've seen, and it can't correct. Right? 2D plus 1 in this case, can it correct a single bit? Well, you need a Hamming distance of 3 in order to correct a single bit. So this could do it. And it makes sense, right? If I told you the received word was 10101, who knows which bit got flipped? I mean, there are so many equally likely alternatives that we don't even bother trying to correct in this case. Okay. So the 2D parity, right? There's a homework problem that says show it can always correct or always detect. Or is it always correct? It always detects 1, 2, 3 bit flips, right? So it has a Hamming distance of at least 4. And there's a case where you can flip 4 bits and you can't detect that bits have been flipped. So it has to have a Hamming distance of 4. Okay, since its Hamming distance is 4, you should always be able to correct 1 bit. If there's 1 bit that flips, you can correct it. And again, we saw that last time, right? When you have 1 bit flip, it sort of indicates this one row in this one column where the bit most likely flipped. That's the one we flip back. I mean, what we're really doing there is where we say that's the valid code word that's Hamming distance 1 from what was received. And what was I going to get to? Oh yeah, when you flip 2 bits, right? There are a lot of occasions where you can't tell where the bit was flipped. If 2 bits get flipped in the same row, or 2 flips get flipped in the same column, you can't pinpoint. There are again lots of valid code words within distance 2 from that invalid code word received. I don't know which one to go to that's closest, so I can't repair the error. Okay. So people got Hamming distance, why it's useful, how you can use it. Okay. A student, when I taught this 2 years ago or 3 years ago, showed me this graphical representation. I thought it was, very. Thought it was very helpful. So, okay. Now we're going to move on to linear Hamming codes. Now you know what Hamming means. So. Okay. So what you want is good efficiency. Everybody remember what efficiency means? It's the number. It's basically this k over n. Right, low k over n, where k is the data, number of data bits, and n is the total number of bits to send k data. And also and good Hamming distance. Right, you could have 1,000, k could be 5 and n could be 20. And if you don't have a really good Hamming distance, what's the point? Right? I mean, there's certain codes you're going to try to send where just a few bits get flipped and you can't correct it or can't detect it. Okay? So fortunately for you, These codes are easy to work with, or unfortunately for you, because if there weren't any that were easy to work with, we wouldn't include them in the class. But since there are some that are easy to work with, we do. You guys got no sense of humor. That was like a joke. Or maybe I got no sense of humor. Right. Or maybe it's just the age gap, because I tell this story every time. First 2 years I was teaching, my reviews came back, said, Professor Rubenstein's really funny. And then my reviews started to say, Professor Rubenstein really tries to be funny. And I'm sure at some point, there'll just be such an age gap that people won't even know I'm trying anymore. That's when the professor gets eccentric. I think that's why professors seem eccentric after a while, is they're still trying to relate to the students. This is hopeless. And anyway. So whenever you have a professor that's really cold, that's the professor who gave up trying to relate. Like they've gone, there are 7 stages of teaching. They're on stage 4, and I don't know what stages 5, 6, and 7 are. I just made that up, right? I mean, there's like seven stages in loss, so there's probably also 7 stages to teaching. All right. Some of you are laughing, so make sure in your reviews, make sure you say Professor Rubenstein is fun, or don't. Just give me high scores, or don't. I mean, do what you think is right, or don't. Yeah. Okay. Where are we? Hamming codes. So here is a 7-4 Hamming code. Which means 4 data bits, 7-bit code words. Okay, so we're going to have what we're going to do is we're going to send the 4 data bits. You actually don't have to send the data bits. Sometimes the code can contain very rarely in network systems, because usually you want to send the data and then some code bits. So if everything checks out, you've already got the data. But you could make it so that no bit is actually just data. It's all just all code bits, which can then be not decrypted, decoded back to the original. But anyway, in our case, you're going to send the data bits and 3 additional bits, 7-bit code words. Yeah, 3 additional bits. Okay, so the 4 data bits are going to be, we'll call them B1, B2, B3, B4, and then the 3 additional code bits are going to be exclusive OR combinations of these data bits. Okay, so you can list out the 16. Right, they're going to be the 16 valid code words. Right, one for every 4-bit data combination. So B1, B2, B3, B4, C1, C2, C3. Some of them are 0, 0, 0, 0, 0, 0, 0 is a valid code word, right? And then 0, 0, 0, 1, 1, 1, 1 is a valid code word, right? And then 0, 0, 1, 0, 1, 0, 1. Okay. So far I'm building a code. I've got Hamming distance 3, right? Because these two differ by 3, right? And I keep going, and I can eventually figure out the Hamming distance of this code. But anyway, 0, 0, 1, 1 is going to be 0, 1, 0, right, etc. People see what I'm doing? Okay. We did that. Okay. So coding is easy, right? Coding a code word is easy. What about decoding? That's actually also pretty easy, right? Take your first four bits, compute C1, C2, C3. If they all come out correct, no problem. If they'll come out 0, no problem, unless, if this is a code of Hamming distance 3, unless 3 or more bits were flipped. Okay? If any bits come out incorrect, now you got to go through and try and find the correct code word, right? So what's an easy way to do that? What's a brute force way to do that? You list out all the valid code words, you list your received code word, and you figure out which one has the minimum Hamming distance away. Okay, but there's an easier automated method, which uses something called can use brute force to detect or correct, or it can do the following. Create your check matrix. Let's call it H. No, let's not call it H. Let's call it M. Okay? And let me just make sure I'm going to do this right. Yeah. M is going to look like this. Well, yeah. Let me make it good. So see, there's something magical about math sometimes. They give you these equations, and you're like, "Woo, I don't know why that works, man," but you know, it works. So I'm just going to use it, and I'm always opposed to that. But I still, you know, I think you should, if you're using something, you should know why it works, right? But I still, for some reason, when I like to teach, sometimes I like to show the magic first, and then explain why. You know, it's kind of like a magician who gives away the magic trick. So you're going to build this check matrix, and it's going to look like this. Okay, so hopefully you see the relationship over here with the code bits. This is basically row 1 has the bits relevant for code bit 1, right? Where this is the B1, B2, B3, B4, C1, C2, C3, right? So C1 is B1 XOR B3 XOR B4. Okay, and similarly, the second row is what's relevant for code word 2. C2 is B1 XOR B2 XOR B4. Okay? Okay, so row 2 is bits relevant for C2, and row 3 has bits relevant for C3. Okie doke. Okay, now I'm going to take my M. Okay, so I've received some code word. Okay. What I'm going to do is I'm going to take my M. So my received code word is some, let's use R1, R2, dot, 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 what is it, R7, right? 7-bit code word. Okay, I'm going to take my matrix M, I'm going to multiply it by my received code word. Okay, we're going to do matrix multiplication. In Galois field 2 to the n. Okay, so everybody knows how to do matrix multiplication in Galois field 2 to the n? No. I mean, well, not really a joke, but I mean, we're really doing this. Galois field 2 to the n, it's abstract algebra, which we don't need for this class. But all this is basically saying is additions are XORs. Okay? I mean, we're dealing all with zeros and ones. So when you have 1 plus 1, it's not 2. It's 0. Okay? Okay? And if your answer, when you do this multiplication, is 0, 0, 0, then the code word is correct. Otherwise, find the column your answer is also called the syndrome. I don't know why. Find the column that matches the syndrome. And if it's the ith column, flip the ith bit. And that's the valid code word. Okay, so for instance, suppose let's pick something at random. 1 0 1 0 1 1 0 is received. Okay? Then I want to do this multiplication. So I take my check matrix. I do my multiplication in Galois field 2. Okay? So top row with this is going to give me 1 times 1 is 1, plus 0 times 0 is 0, plus 1 times 1 is 1, so I've added 1 and 1. That's 0. Okay? Plus 0, plus 1, so I'm at 1, plus 0 plus 0. So my top bit's a 1. Right? Next row. 1 plus 0 plus 0 plus 0 plus 0 plus 1 plus 0 is 0, right? I had two 1s. So I XOR them together, I get 0. And then 0, 0, 1, 0, 0, 0, 0. So 1. Okay? So that's my code word that's received. I compute this syndrome. I get 1, 0, 1. So I know it's not a correct code word, right? If the correct, suppose this was the right data, right? The correct code word would have been 1, B1, B2, B4. Oh, B1, B3, B4, sorry. It would have been 0, 1, 2, 3, and 4. 1. 0, 1, 1 would have been the correct code word, right? 1, 0, 1, 0, 0, 1, 1. I think I just said. That would have been the correct code word if those 4 bits were the correct data, right? Okay, so now all I'm saying is, okay, here's my syndrome. So find the column that matches the syndrome. That's the third column, right? So I flip the third bit. So the correct code word was I'll put probably in parentheses. 1000110. 110. Okay, I flipped the third bit, right? And now you should see that yeah, that's you can check that's the correct code word. Okay, it's Hamming distance 1 from the original from what was received. All right, so in a code with Hamming distance 3, it's the most likely. So that you can check that this is a correct code word, right? Take the 4 data bits, you'll get those 3 check bits using that code. I said, suppose I'm the receiver and the sender sends me this. Okay. I mean, I can quickly do a check and see it's not the correct code word. Why is this the correct code word? Or why is this most likely the correct code word? Because it's the valid code word that's the minimum Hamming distance from the code word I received.
Basically, I guess you took the code word you received and put it up against the valid code words and found which one was closest.
You could. That's the brute force method. Right? You'd have to look at all the valid code words and find the one that matched. I just did this process I described over here. Do the matrix multiplication, find the syndrome, find the column in the syndrome that matches. Find the column that matches the syndrome. It's the third column, so I flip the third bit. That's the automated process to do this.
So, but just looking at one bit.
Yeah. Well, the code is Hamming distance 3. Right?
Oh, okay.
Means I can only correct 1-bit errors. So if I have more, so the reason I say probably is it's possible that the original transmission was the original transmission could have been all zeros, and 4 bits could have gotten flipped, and I just so happened to get 101011 and I would have decoded it incorrectly. But under the assumption that lots of bit flips are very unlikely. The probability of bit flips is very small. This is the most educated guess. Yeah?
How do you come up with your check matrix? How do you create your check matrix?
Again, row 1 kind of corresponds to the code over here, right? The C1 bit uses B1, B3, and B4. And if you look at how I set this up, this is the B1 column, the B3 column, the B4 column, the C1 column, C2 column, C3 column. So C1 really doesn't involve C2 and C3, but it uses B1, B3, and B4. Okay. I haven't explained why this works. I'm going to do that now. Yeah, Ron.
Generate your matrix however you want, as long as it follows the rules.
You can
generate your check matrix however you wish, as long as it follows the rules. Like you could pick any arbitrary B1, B2, B3, right? And then you just have to make sure that C1, C2, and C3 were the XORs in the right way.
You mean you could arbitrarily choose how to generate your code?
No, you can arbitrarily choose how to generate the exact matrix you use to check. In that it does have to be part of the code, but there are 16 possible code words, right? And you're only using 3, right?
No. These are not necessarily. They're 7 bits long, but they're not necessarily. They may be valid code words, but that's not how I'm choosing them. This is okay. If C1 equals B1 XOR B3 XOR B4, I have to put a 1 in the C1 column and in the B1, B3, B4 columns. You have to do it this way, and let me explain why. Because it's really, I mean, I think it's kind of neat that it works, but it's not very hard to see why it works. So the first observation is that when I say, okay, why it works. And just so you know, when I ask questions on the midterm, I assume you know how to do it. Okay, that's like part A of the problem. Part B is going to be making sure you understand why things work. And that's really what I care about. I don't care if you're able to apply the techniques. I care if you understand them. So whenever I ask questions on a midterm or final, I always throw in some twist. And I have passed midterm. I'll hand them out before I give out the midterm, but you'll see. It's never just, compute the 2D parity check of this. It's like, what if I change it like this? What if I do this? What if I manipulate it like this? Is this a valid Hamming 7/4 Hamming code? So you got to understand what's going on, right? So why it works, in other words, is important. Okay, so why it works. C1 equals B1 XOR B3 XOR B4 is the same as saying what? C1 XOR B1 XOR B3 XOR B4 is 0, right? If I XOR anything with itself, I should get 0, right? 1 XOR 1 is 1, 0 XOR 0, sorry, 1 XOR 1 is 0, 0 XOR 0 is 0. So if I tell you that this equals C1 and I XOR that with C1, you got to get 0, right? Okay, and the same thing for the other ones. So what are we doing when I'm asking you to multiply a row? Okay, you are the ones here are selecting the terms in this received code word that I'm looking at, right? So for instance, here I've got B1, B3, and B4, and C1. So I'm saying take B1, B3, B4, and C1, right? And exclusively OR together. And do you get 0? Or what do you get? In this case, I got 1, right? But I should have gotten 0 if they were all correct, if none of them were flipped, right? Hence, having something that's not 0 here is a mistake. Okay? People with me? If any of these values come out as non-zero, when I did the appropriate multiplication, the second row was saying take the first bit, the second bit, the fourth bit, and the sixth bit. Okay, what should have been B1, B2, B4, and check bit 2. When I did this multiplication, I was just exclusively ORing them together. Again, there's no problem with the code word, with the received code word. That should come out to be 0, right? And it did in that case. And then I did the last one for checking whether the I constructed code word C3 worked, and it didn't come out correct. Okay. So I got this 1, 0, 1. So I know it's not correct. Okay, people understand that? Yeah.
You might get a 0.
Yeah. Well, this is a Hamming code with distance. No. If 2 bits are flipped, I won't get a 0. The Hamming distance of the code is 3. So you come up after class and you can show me the 2 bits you flip. And I'll show you I don't get 0, 0, 0.
Okay, wait, actually, how did you get Hamming distance 3 again?
And list all the valid code words,
And
and look at the Hamming distance between the pairs, and you'll see that there's at least a distance 3 between any.
I thought there was a quick way that was 3.
No. Well, I know that it can. I know that this code will correct 1-bit flip and detect 2-bit flips. So I know it corrects 1, so it's got to have it always correct 1-bit flip. So it's got to have Hamming distance at least 3. And you've only got 3 extra check bits, so it can't have Hamming distance more than 3. Okay. So that's how having non-000 here does a detection. Now here's something else I want to show you. Suppose I change one of the bits in the received code word. Okay, suppose I make this third bit a 0. What have I done to this multiplication? I mean, another way to look at this multiplication. I mean, we went row, row, row. But another way to do it is to say let me redraw it. So I've got these 3-bit components, 1, 0, 1. What's the next one? 1, 1, 1. Okay, and I've got this B1, B2, sorry, R1, R2, up to R7. Okay, and if R1, another way to look, the way I compute the syndrome is if R1's a 1, I'm going to add this column to the syndrome, and if it's a 0, I just don't add in that column. Okay, so when this is 1, 0, 0, 0, 1, 1, 0, what that's saying is I choose this column, right? I choose this column and I choose this column, right? I match up the ones. I'm XORing this column with this column with this column. Okay, but before we did the computation, you did it row by row. We do it column by column. You're going to XOR this column and this column and this column, right? If I flip a bit here, I change whether or not I include the column. Okay? If I change whether or not I include the column, the syndrome changes by basically you XOR that column into the syndrome again. You either unXOR it or you XOR it another time. It doesn't matter. Those two operations are identical, right? So if I change the 3rd bit, I'm going to XOR, if I change it from 0 to 1, sorry, this was a 1 originally. The original code was like that, right? Oops. The original code word XORed these 4 columns, right? If I change this bit, I no longer XOR this column. Okay, so I have some quantity A that's XORed with this column to give me 1, 0, 1. If I no longer XOR this column, right, it's like I'm XORing the syndrome with another 1, 0, 1. So I'm going to get 0, 0, 0. Hence, I basically want to XOR the syndrome with 1, 0, 1 to get a valid code word. The easiest way to do that is to flip certain bits to include additional columns for XORing. In this case, I just do it with column 3. In fact, there are 7 possible outcomes that are not 0, 0, 0 here, right? There are 7 columns here, and each column has one of those possible outcomes. So there is some column which if I XOR an additional time or one fewer time, I can change this to be 0, 0, 0. And that's basically picking the bit in this code word to flip to give me 0, 0, 0 for my syndrome. Okay? Now it's possible, suppose this. I didn't say much here. I did it mostly verbally. Suppose I tell you 1, 0, 1, 0, 1, 1, 0 was received, but 2 bits were flipped. Okay, which 2 bits? You can't say for sure because it's a Hamming code with distance 3. But we can figure out what are the possible combinations. So now we need to have 2 bit flips, okay, that would have resulted in a syndrome of 1, 0, 1. Okay, so if the 3rd bit flipped by itself, that would give us 1, 0, 1. Right? But I'm talking about 2 bit flips here. So it could be that the first code bit and the 3rd code bit flipped, right? Those XORed together would give me 1, 0, 1. So if I flipped those, I would get 1, 0, 1. Or the first 2nd bits, those 2 flipped together would also give me a syndrome of 1, 0, 1, right? Because this column XORed with this column gives you 1, 0, 1. Or the 4th and the fourth data bit and the second check bit also would give you a syndrome of 101? Okay. Any questions? Who thinks they understand this? Okay. So for everyone else, office hours, ask your friends, think about it some more, sleep on it. That's it.